to turn it over to Dr. James Rickles here, the director of the Atlas facility, to introduce our speaker for today. So, Jim, it's all yours. Thank you.
Yeah, thanks, Tommy. So I want to welcome everyone to our presentation today, which is part of the NHERI Lehigh Webinar Series. We have a special guest from New Zealand, and I'll introduce the person in just a minute here. But let me just make a note of the fact that the seminar series is one in which we hold roughly each month, and it gives an opportunity to have researchers talk about their work and how it relates towards natural hazards. Our particular site specializes in natural hazard engineering, particularly with large-scale structural testing. And with that, I want to introduce the speaker. The speaker is Professor Geoff Rodgers. He's from the Department of Mechanical Engineering at the University of Canterbury. That's in Christchurch, New Zealand. He's actually a little bit closer than New Zealand today. He's visiting us today, so we have a special guest as well as a good connection here. And so Geoff's going to talk about some of the research he's been doing for a number of years, and the presentation is titled Energy Dissipation and Supplemental Damping. You'll see the importance of this in just a moment. And it relates towards lessons learned from device development and testing in large-scale structural tests. So before we actually start the seminar, and Geoff could take the podium, sorry, let me just give you a little bit of a background here on Geoff. So as I mentioned, he's from the University of Canterbury in mechanical engineering. In his research career, he's focused on developing some novel seismic damping devices and furthermore implemented them in terms of developing strategies to support low damage structural design. So that's basically resiliency under seismic loading. Now, he's been very busy besides doing research. He's the immediate past president of the New Zealand Society for Earthquake Engineering. And that particular society is one in which they promote and advance earthquake engineering in New Zealand and support the translation of research to practice. In addition to the work here presented, he's also done work in both computational experimental studies, looking at building instrumentation and monitoring, in addition to large-scale experimental testing with a number of collaborators, both within New Zealand as well as internationally. It includes China, the United States, and Canada. So with that, I'm going to go ahead and hand the podium to Geoff. And as Tommy mentioned, if you have any questions, feel free to put those in the chat, and we'll address those at the end of the seminar today. Okay, thank you. So Geoff, welcome to the seminar series. I'll hand the podium to you.
Oh, thank you very much, Jim. So as was mentioned, I'm actually visiting Lehigh University. I was here last week and this week. I was fortunate to get a small grant for the New Zealand side last year to catalyse some closer relationships between University of Canterbury and Lehigh. So sort of this week at least, I'm kind of an honorary extended family to the NHERI group. So a big thing that's motivated a lot of the work in New Zealand, and particularly the uptake of some of the research, has been the earthquakes that we had through 2010 and 2011. So in Christchurch, we had a significant earthquake in September of 2010, and that was followed about 6 months later by a significant earthquake in February 2011. So together they caused a lot of damage in the Christchurch CBD and led to a lot of demolition. So we have traditionally adopted the sacrificial design approach. It's been used fairly widely worldwide. It's really based on the hierarchy of strength, the capacity design, and protecting the columns through the formation of a hinge and the beams. So something I'm sure you're all very well aware of. But certainly in the wake of the earthquakes in Christchurch, when you had engineers going to the media and doing interviews and saying that this is the type of damage that we would expect to see in an earthquake, that was something that certainly gave the public a cause for concern, and it's very clear that there's this significant disparity between the way we've traditionally designed buildings and what the public actually expects of the performance of their infrastructure. So, separate to what I'm talking about today, but there's also a separate project which has been run, funded by our state earthquake insurer, in New Zealand, which is Natural Hazards Commission Tokatoake, and they're looking at the society's perception of expectations of building performance. So that just sort of quantifies and supports this disparity between what the public expects from our buildings and what we tend to actually be offering in a lot of cases. This was Christchurch a few years after the earthquake, so there's a significant amount of demolition there. It was around about 40 billion New Zealand dollars, so yeah, 25 billion US dollars. The city suffered from it's a city with a population of about 400,000. There's lots of things that contributed to this, insurance penetration and all sorts of contributing factors, but a significant amount of the CBD was demolished. So obviously the onset of damage and that sort of second response regime that occurs from the sacrificial damage, it has a lot of advantages. It reduces the stiffness, lengthens the period of vibration, which then moves to generally a lower period of demand on the response spectra, reduces accelerations and absorbs energy, but obviously the structure may not recenter and a significant downtime and cost. So that sort of has motivated a lot of work that's been done in New Zealand and internationally around the world around the sort of jointed rocking connections and the ability to provide, whether it be base isolation or like the press systems, the jointed precast concrete systems, really ways of providing some sort of controlled motion here rather than through the formation of damage. So this was actually a large-scale structural test. It's just an external beam column joint that was used to simulate the connections, and this was actually part of my PhD. So this is going back nearly 20 years now. So a small amount of gap opening that occurred there, and obviously it has significant impact in terms of how the building interacts with the earthquake. Now, you can see, I'm sure if you can see my pointer, there is a steel tendon which is unbonded to the concrete, clamping everything together, and then below that certain level of demand, you have this rocking. Now, this particular connection is what we refer to as a tearing solution, and that it does have a frame dilation issue. And if there was a floor slab that ran continuously across that, then it does induce a dilation effect on that floor slab. So there is some continuity issues with that particular design. And in that particular building and that structural subassembly, what we looked at was a way of absorbing energy in that. So we wanted a high force capacity, a small device volume to fit directly into the jointed region. We wanted large and elastic displacement capacity, but we didn't want any stiffness or strength degradation or any low cycle fatigue concerns. So one thing we actually applied there was the concept of a lead extrusion damper. So this is actually some photos. This was from the 70s, and this was developed in New Zealand. It was the extrusion device, and these two devices, one was 700 kilonewtons, one 100 kilonewtons. They were quite long stroke devices for base isolation purposes. And the principle behind them is that you have essentially either a bulged central shaft or a constricted outer tube. And regardless of how you do it, you're essentially creating an annular restriction, and you're plastically extruding a plug of solid lead backwards and forwards as you move the piston on the shaft relative to the outer cylinder. So much like making Play-Doh spaghetti, where you're extruding through that die, except you're doing it in a reversible way, and it's actually an annular orifice that you're using. So the question was, why do we use lead? It's not the world's friendliest substance. It obviously has some toxicity issues. Well, the key thing is that lead has a recrystallization temperature of about minus 35 Celsius. So when you're working this at ambient temperatures, it's essentially like when you're hot working steel at 800 to 1,000 degrees Celsius. So essentially you're not seeing any stiffness or strength degradation. The grain structure within the material is dynamically recovering, and that can all be done at room temperature, which is why lead has these unique rheological properties, which make it a good candidate material. So for those jointed connections, we made some devices here. So they were 120 kilonewton 12-ton resistive force in the top and 25-ton in the bottom. So when you do put that in and you pressurize the lead in there, you can actually get quite a significant amount of force capacity in a very small volume. So that's a very favorable aspect. The devices do have a slight velocity exponent, so they have a velocity dependence with a velocity exponent of about 0.1. So in some ways they're broadly similar to a hysteretic damper, but they do have this sort of weak velocity dependence. Now, with a velocity exponent of 0.1, there's not going to be a big force difference between two dynamic tests. But if you compare a quasi-static test to a dynamic test, which we have here, then there is a reasonable force difference. So what we have here is just the same device being tested in two different test machines. The inner blue loop was a quasi-static test, which was actually just a triangular wave. And then the red loop was a dynamic test, which was actually a sine wave. So while the force limit increases, the shape of the loop also changes. And that's traceable back to one being a triangular wave and one being a sine wave. So there's the blue one essentially is a constant velocity being put into it, and then the red one is a varying velocity with displacement. So what you can see there is you're getting about 100 kilonewtons at 10 millimeters per minute, or about 0.16 millimeters per second, and then about 150 kilonewtons at 30 millimeters a second. So you're seeing about a 50% increase when you change this input velocity by about 160 times. So there is a velocity dependent component to these, but it is relatively weak. Comparing a quasi-static to a dynamic test has quite a significant difference, but comparing between two quasi-static tests or between two dynamic tests is relatively minor changes. At the other end of the spectrum, this was actually a device that I worked with. It was to the building in Christchurch, and this was a 70-ton resistive force with a 5-inch stroke. So rather than being quite a compact device, this was much larger. The largest size of this device was really dictated by the length of the stroke that was required and all the attachments. So essentially the buckling of the central shaft had to be quite large to prevent buckling, and everything sort of scales up around that shaft, which is why that's quite a lot larger than the other devices. Viscous fluid dampers, I'm sure you've all seen these. Anything from a linear force velocity response to a nonlinear force velocity response, so they're fairly standard. And then one thing we've also looked at is the ring feeder friction springs. So these are an alternating taper. When you put an axial compression onto the stack of springs, the outer rings actually undergo a radial expansion, and the inner rings undergo a radial compression. And in doing so, you get a very, very high stiffness spring. So you're sort of turning this axial force into a radial reaction, and the stiffness of these springs can be orders of magnitude higher than you would get from something like a coil spring. So while coil springs are very useful for sort of mechanical plant, they just don't tend to have the stiffness that would be useful on a structural scale. They don't have the ability to get the sort of forces we need. So that's why these are a favorable option. They're just a commercial product. And you can also apply some preload to them, as is shown in the diagram here, where essentially it's a force threshold beyond which they don't move, and then there's a sort of a triangular flag-shaped hysteresis from there. That hysteresis within the loop is due to sliding within those ring elements. Now, one thing we've done is looking at a device here, which is a combination of these. So this is a device, it might look at initially looking at the diagram here, the tube that sticks out the right-hand side here has ring springs located within it. It might look like it's in series, but those two elements are actually in parallel, and then they undergo the same displacement, and the forces in the two damping components, the viscous fluid component and the ring springs, actually add together to generate the total damping force. So this is the device that results, and as you can see, as you go faster and faster, you get a much broader loop, and as you go slower and slower, you just revert back to the ring spring behavior as you saw on the previous page. Another thing we've done is looking at custom quadrant damping. So this is sort of born out of a lot of the semi-active device stuff, the resettable stiffness devices and the magneto and electrorheological devices. There's a huge body of work that's been done there. And I've actually worked previously on some resettable air dampers. But the key thing is that the semi-active devices do have some complexity to them. So the question was, can we achieve that same broad type of behavior, but can we do it in an entirely passive way? So we don't have to have any computation, any sensors, any power requirement. We've just got a passive device that will produce that behavior. So the idea is that the damping in specific quadrants of the force deflection plot may mean that we can provide damping to a structure, but without leading to an increase in the overall base shear. So in terms of peak axial forces and columns and the demand on the foundation, this has a potential advantage here. So this is sort of the schematic in terms of if you have a linear elastic structure. So the previous slide showed a bilinear elastic structure, which you might see for a rocking structure. If you've damped something to the point that you're sort of largely within the linear elastic range of the structure, the idea here is that you can bring in your displacements, but without increasing base shear. So depending how much you reduce your structural displacements, you may actually see a less total base shear in the other cases as well, but this would further bring down the combined demand on the foundation. So the question about how to achieve that, we've got a standard viscous damper that can be fitted within a cylinder, so that's what that might look like there. The first thing we did was to put essentially a plate which covered, so we've got some small inner orifices in the piston, and then we've got a much larger ring around the outside with much larger orifices in there. So we have this one-way valve, which is just a large circular washer, which closes those larger washers. So when we're pushing in the direction of the washer closes down and closes off those larger outer orifices. But then we're turning in the opposite direction, that washer lifts off the outer ring, and you get much more open fluid path, so you get very little damping. So in this case, that would give you 1/2 of the deflection plot. That's basically 1/2 of the damping behavior that you'd see from a conventional viscous damper. The other thing we can do is to actually taper the cylinder of the device. So essentially, as the piston moves through the narrower part of the cylinder, it produces damping forces. But then as we move to the wider part of the cylinder, there's actually an alternate fluid path around the outside of the piston, between the piston and the cylinder. So there's an annular gap there. So if we implement that, what we can essentially do, depending how we orient the piston relative to the step in the cylinder, we can essentially get one quadrant of the damping response. So those 4 plots are actually experimental results, and then we have the sort of 4 configurations that they correspond to relative to how you orient the cylinder and the piston within that cylinder. The next thing was to try and say, we don't necessarily want one quadrant, we might want two of the opposing diagonals. So in that case, what we have there is actually 2 pistons with one-way valves on them, like we saw a couple of slides ago, positioned back to back, and they slide initially through a narrower central section of the cylinder, and then they pass into a wider section. So together, that gives this sort of 2-4, so the off-diagonal damping to the quadrants. So initially, as we move out this way, this piston is in the narrow part of the cylinder, but the one-way valve is open. When we reach the peak displacement and start going back, the one-way valve closes, and the piston was initially in the narrower part of the cylinder, produces damping through that quadrant, and then as we pass the nominal 0 position, that one piston that has the one-way valve closed passes into the larger part of the cylinder, and then at that point the damping force drops away. We've also looked at some tension-only bracing, which is just looking at different engagement mechanisms. So this is actually, in this case, it was a yielding steel fuse was the dissipator, and looking at that as a way of absorbing energy, say on a rocking wall, when you've got uplift, but you've got no residual compressive forces, such that you don't then start to offset the restoring force that may exist from either gravity or post-tensioning within a rocking wall. When we test that, you essentially get because it was in that particular device, it was a yielding steel dissipative element, then we end up with sort of this piecewise monotonic behavior. So you can compare here the green greeny grey line is actually essentially the piecewise monotonic behavior of the fuse. And then the blue line is the observed system response, which is essentially every time you ratchet, you reset the zero displacement datum, and then you get the more compact loop there. So it's just a way of providing fairly immediate resistance on uplift and not having to overcome elastic deformations or residual compressive forces. Another thing I've looked at, this was a project with the University of British Columbia in Vancouver, was looking at a lead extrusion device like this, but incorporating that into essentially a telescoping brace. So it looks externally a little bit like a BRB, but you've essentially got a lead extrusion device in there. So that means you can sort of tune stiffness independently of strength, because you can size the steel components independently of the bulge, which then dictates what the resistive force during loading is. And then the next thing we also did was looking at putting some ring springs into the open cavity within the tail of the device to provide a small amount of restoring force there. So this wasn't about providing an overall recentering device, just because the size of the ring springs that would be necessary to do that would be very large relative to the forces provided within the lead device. But the key thing is that it was enabled us to tune, this is the experimental setup in which they were tested, that enabled us to sort of tune the post-yield stiffness. So we have a yield stiffness defined by the bulge size in the lead device, and then also have a post-yield stiffness that could be dictated by the this particular ring springs that we used. So that was just a way of being able to tune and customize the response behavior. So a few things we've done, like this was just a bit of rocking connections. We're actually embedding the lead extrusion device within the end zone of a beam column connection. And rather than having an external device, this was embedded and cast into a cast in situ closure pore. There was still separate jointed connections, so that this wasn't a monolithic solution. It was a precast beam and a precast column that came together and then had a cast in situ closure pore in the end of the beam. So you could connect everything up, and then the final joint there just looks like a standard connection. It's just got some displacement gauges mounted there. As we tuned the clamping force provided by the post-tensioning, we've got 4 different results there. And we also, after we'd done quite a few testings, we opened up the joint, we cut off the damper connection, and then also got the baseline result there for the different drift levels. So this is sort of a parametric study with and without damping, and with different levels of post-tensioning within the connection. We also did increasing and decreasing drifts. Just essentially, we saw largely the same response, which was doing the big cycles first rather than the small cycles didn't really change the overall response of that connection. We did try a steel connection, so this was a top hung beam column joint where essentially the top angle was providing a pivot point, and then we used the damper to form an overall moment connection. Should be a video of that. It was a quasi-static test. This was a sped up video. But the damper sits down here below the bottom flange and provides the overall moment connection. So we tried a few different configurations there with different number of devices in different locations, but essentially we got a fairly reliable, it's two fully reversed cycles at every drift level here. And we got a pretty good, pretty consistent elastoplastic response, but without any damage to the steel structural components. So there was quite a good low damage steel connection. We've also tried previously incorporating the lead extrusion devices into a rocking glulam or mass timber wall. So the lead extrusion devices were acting as hold downs between the wall and the foundation. And this was the test here in the lab. And then this is the overall response there. So a little bit more flexibility given the nature of the timber, but actually quite a good overall result there. So then I just want to talk about some of the system level dynamic shake table tests that we've done with this technology. So I've actually been fortunate now to be involved in three different tests that have occurred actually in the same test lab here in China. So this is the Tongji University labs. This is the earthquake engineering test hall in the Jiading campus in northwest Shanghai. And it's actually primarily a bridge lab. So it's got a long trench that the four shake tables sit in. And that means that you can set them up to sit underneath piers of bridges and do dynamic bridge tests. But you can also put the tables together and use them as a combined shake table to support a building, which is what we've done. So this was the building. This was with a number of collaborators with Rick Henry at the University of Auckland, Ichu Lu, who was University of Auckland at the time, is now a faculty member at Tongji, and Professor Ying Zhou at Tongji. So the idea here is that in the longitudinal direction, we have a reinforced concrete rocking wall. It's post-tension to the foundation. And in the longitudinal direction, it's actually linked into the floors through a flexible link slab. In the transverse direction, we actually have a mechanism here. So the wall is vertically isolated from the structure, and there's no uplift of the beams or flooring as the wall rocks. But in the longitudinal direction, because they are integrated, the rocking wall actually uplifts the floor through that link slab as it rocks. So we used longitudinally hung double T concrete on the first floor, and then we used transverse metal tray of the comp floor, the composite steel tray, for the flooring in the upper level. So there's a couple of different design configurations. One was to provide 10% damping and have 1% design drift. The other one was to have 5% damping and a 2% design drift. And that was tweaked by modifying the post-tensioning and the amount of energy dissipation. So both the strength and energy dissipation and damping provided through that system. So this was the structure here in the Tongji lab. So that's Rick Henry and Ichu Lu there, staying at the time. At the time of that, they were both in the University of Auckland. So you can see the comp floor composite steel tray here, and then you may just be able to make out the double T's running longitudinally through here. For the beam column connections in the structure, we actually used a design that was developed, it's called the slotted beam connection. It was developed primarily by Des Bull. He's essentially an adjunct professor of concrete design at the University of Canterbury. He's also a practicing structural engineer. But the idea is that there's essentially a hinge point up here, and the beam is actually cut back here to allow both positive and negative joint rotations, but to do so in a way that doesn't create frame dilation, so that there's no dilation of the columns and there's no tearing or displacement compatibility issues induced within the flooring unit. So that's a key difference from the connection that was developed before. In this situation, we had a few different configurations and design situations. We had, in this particular case, we have the yielding steel fuse. That's essentially like a scaled down mini BRB. And we also had a configuration where we put a lead extrusion device in here as a means of forming that moment connection. So that's sort of the equivalent of the steel connection video that I showed you previously. So that's the connection there with the lead extrusion device mounted, and you can see the cutback in the column. So this was the structure here. Being tested is about 9 meters tall, and it had a 10 meter by 6 meter footprint. And then this is just a video of the testing. So you can see people here at the left-hand side and right-hand side. They are, yeah, it's a pretty big test. So just show the video here. This is just a different view of a shake. This was actually in the design 2 configuration where we had slightly less damping, a 2% design drift target, and this was at MCE level. Um, this was actually three of the viscous dampers that were mounted into the longitudinal wall. So, sorry, this is actually the transverse wall. In the longitudinal direction, we had a more lightly armored wall, and it actually sat on top of the foundation. And in the transverse direction, the wall was actually recessed into a tapered steel pocket to provide shear resistance. And this is just the localized view of the viscous dampers operating as the wall uplifts. So in that configuration, there was a little bit more flexibility in the base plate. So the base plate itself was reasonably rigid, but the anchoring of that base plate into the foundation was not quite as good as we would have liked. There was all sorts of physical reasons why we perhaps couldn't do better there. But it is just reinforces the idea that the total displacement demands that you're putting into viscous dampers like this is relatively low. You're not putting half meter displacements in. That tends to be on the order of sort of 10 millimeters or so. So then trying to design all those connections to be relatively rigid and minimize the elastic flexibility such that the largest percentage of displacement goes into the device itself and actually absorbs energy and does the job that you're trying to get the dampers to do. The other thing, just something that's often overlooked is the in-plane and out-of-plane demands on the wall. So when this was a connection for the viscous dampers, we actually had spherical bearing connections in there. So when you rock in-plane on the left diagram there, you've got much larger displacement demands into your dampers. You also have a rotation compatibility issue. But in the out-of-plane direction, while the dissipation, so the eccentricity to the point of the dissipator is much lower, and therefore the axial displacement demand on the just on the dissipator is much lower. There's still that rotation demand on the connections. So that's why we did focus on having spherical connections there. When it came to the steel fuses we used in that same location, we did actually mount those rigidly, and then, because that was a piece of steel that was actually being elastically deformed or plastically deformed, there was enough sort of transverse rotation capacity to sort of accommodate that and not have to use spherical bearings. But because the viscous dampers are much more rigid relative to the loads they carry, it would be inducing significant sort of prying effects and other unintended demands on those dampers if we didn't have the spherical connections there. This was the rigidly mounted steel fuses in the wall base. A little bit of damage on the wall there, just a little bit of spalling at the wall toe. That was after about 38 different earthquakes that we'd put the structure through. So it wasn't actually looking too bad given the demand, the cumulative demand that had been subjected to. This is actually a video of the interior of the first floor of the first elevated floor of the building. And what's highlighted in red there is essentially the area that's covered by the link slab, so that the double T's stop short of the wall, and then there's just the link slab, which is the topping component, goes through, connects in, and provides diaphragm action into the wall, but has can separate from the double T such that we don't over constrain things, and there's definitely some cracking on that floor, but nothing of significance. So. This is actually a video which sort of shows the demand on that floor quite dramatically. So while there is quite a lot of out of plane, compatibility displacement demands in there, by just having that designed to have some flexibility in the out of plane direction, that actually results in some pretty good behavior. This was Rick and Ichu after the end of the testing. Pretty happy with the building. And then one thing that we did towards the end, this is sort of a focus for me, and I'm biased because this is my area of interest and passion. But the last thing we did was we took all the energy dissipation out of the building, and we just shook that as hard as we could. So there's a few reasons for doing this. The main one was to try and get as much displacement demand. So we'd gone up to about 2% drift. This was to try and we'd already reached the overturning moment capacity of the table. The table had actually shut down. The control system had shut down the table on one of the tests. So this was one way of getting more displacement demand into the structure, without being able to, not having the ability to increase the shaking intensity we subjected it to. So we got this, subjected it to a bidirectional test, and we got up to just beyond 3% drift in the building. So this one, as well as being a larger drift, also has no energy dissipation incorporated into it. So while the energy dissipation is a relatively small part of the structure in terms of the size and the mass and things, it did have a significant impact on the result, both in terms of a larger peak drift and then a much longer shakedown at the end. So if we actually plot that and we look at the displacement traces for the same building, the design two is actually subjected to a higher demand motion and then a lower demand for design three. But you can see there the peak displacement is larger, and then the shakedown, the duration of that to come back to rest was much longer. I was also fortunate to be involved in what was referred to as the robust steel project. So this was a low damage steel frame. There was a number of different connections and things that this was done. It was a very complicated building to accommodate a lot of different tests and a lot of different design configurations. But the one that I was particularly interested in was the rocking frame and the transverse direction. So you had two rocking frames at each end, and then we had a tension-only dissipative element on each end, on each side of each wall, and that provided resistance. So it was a ratcheting engagement mechanism and a yielding steel, sorry, a sliding friction element to provide energy dissipation. So this was some of the details we had. Essentially, this is what we sometimes refer to as the grip and grab device. There was the tension on the right there, the ratcheting engagement mechanism at the top, and the sliding friction component at the bottom. You have the rocking frame, and then this was some component testing we did on that device at the University of Auckland in the middle of 2022, just to prove the device worked before we put it into the large shake table test. So there's essentially a toothed rack. It was just a piece of steel with some teeth cut into it and then a ratcheting mechanism. And then this was the sliding friction component at the bottom. So this was the actual full steel test. Similar sort of same shake table, same facility as the previous test. But this was again about a 10 meter by 6 meter footprint. It was a little bit taller because it was actually a 3-story structure, but it did have a slightly lower interstory height. And then the third test, which actually finished in January of this year, was a scaled down high-rise test. So that was actually a coupled rocking core wall with outriggers, and then that was there was energy dissipation devices mounted within the outriggers and within the wall base. So this was a test that was set up in January of 2020, and we were well advanced with the planning. We were planning to test a few months later. Of course, the pandemic hit and sort of put the trail on things. So we fast forward 5 years after the pandemic passed, we managed to resurrect the project, got it onto the shake table, and this is sort of a example of that testing. So, So also, so that's an ongoing project, only being a few months since we finished that testing. We're still going through data and pulling out all the interesting aspects of that test. But we certainly saw some really interesting things in terms of that building responds as a coupled rock and core wall in one direction, and it operates as an outrigger core wall in the other. And it's subjected to many transverse unidirectional motions and also two bidirectional motions. We have seen some deployment of these ideas in Christchurch. So this was actually a hospital that was rebuilt after the earthquakes. It was mainly built in 2012, 2013, and then opened in 2014. So that was actually a 8 pairs of rocking frames around the perimeter, and they had post-tensioning, they had BRBs between the two walls, and they also had lead devices between the uh, rocking walls and the foundation. So these are the steel rocking walls that were applied. They sat within a steel shoe to provide shear resistance, and then they were isolated, vertically isolated from the beam to prevent any floor hogging, floor uplift issues as they rocked. So that was one building. There's also the Turonga, which is the Christchurch Public Library. So they had reinforced concrete core here, a steel gravity frame, and those rocking walls here, they actually independently rocked in the two transverse directions. So they weren't coupled in the two, they weren't directly coupled to each other in the orthogonal directions in those cores. There was also viscous dampers, so dampers mounted between the wall and the foundation, and one of the former PhD students at University of Canterbury developed low damage base connections. So this is looking at sliding friction base connections at the column bases. So rather than having a hinge form by yielding the column, it was actually just having some controlled rocking motion in the column. That was actually his PhD. And then he went on to apply that as a design engineer for this building. There was also U-shaped flexural plates between those two orthogonal walls and the core, and then lead extrusion devices between the rocking wall and the foundation. So that was the building there that lit up in the evening. And then finally, one other building that used the devices, the lead extrusion devices, was a low damage structure in the Mission District of San Francisco. So this was a building by a community developer that was for formerly homeless people and those with sort of below half the average median income for the region. So the idea being, while we talk about resilient buildings, we often think about a server farm or a hospital or a really high value critical asset. I was fortunate to work with David Marr and his team at Marr Structural Design. His thinking here was that for some of these people, they don't necessarily have the same level, a great deal of resilience in their personal life. That if they have been formerly homeless, they perhaps don't have a great support network around them. And this was about trying to compensate for a potential lower level of resilience for the people by incorporating a higher level of resilience into the building. So this had some rocking walls throughout the building, and they actually rock instead of between the wall and the foundation. They actually rock between the foundation and the pile cap. So it's just moving the rocking a little bit lower. And this was the sort of conceptual design. This was the dampers mounted, anchored to the top of the pile cap at the bottom and then into the foundation at the top. And then this was the final building here. So that was actually off. It was on a very tight budget because it was a community housing project, but that amazingly did actually get a gold rating by the US Resiliency Council for that work. So I guess that concludes the talk. It was just I've had very fortunate to have worked with some amazing people and some great practitioners on a few different projects and contributed my small piece to that. So maybe if we conclude things there and have a little bit of time for questions.
Well, thank you very much, Geoff. Are there any questions? I guess we can go to the chat. And let me open up the chat and see what's here.
There's no questions at this time, but usually at the end, we give people a few minutes to formulate any final thoughts or questions.
Yeah. So, Geoff, I have a question here. You showed the shake table tests and other applications. I assume there's a performance-based design procedure that otherwise it's just a stroke of luck, right? What's the criteria? Is they designed with the damping in mind that you have a procedure there? Have they developed the procedures there to implement your devices?
So the yeah the for there's three different designs there. The first concrete one, essentially, it was done based upon sort of a yielding steel behavior. So we did have three different design configurations. One which used steel fuses as all the dissipative elements everywhere. One that traded out the lead extrusion devices for the steel fuses in one location, and then one that used traded out the steel fuses for viscous dampers at the wall bases. So essentially what we've done was looking at designing it based upon yielding steel at those locations. So then that fits much more easily into conventional design practices, and we just used some damper equivalents and area-based calculations in there. But we also did some performance-based engineering and some numerical simulation to sort of prove the design before we went into the shake
Mhm.
tape test as well. So, but yeah, certainly I think there's definitely ongoing scope for to simplify that process. As someone
Yeah.
said once, a practicing engineer said to me once, academics are great at coming up ideas where all you have to do is change everything about how you design a building and then they work great.
Yeah. So the other question I have is what caught my attention there was the I guess it's the longitudinal direction. John Stanton may have a similar question on this, which I'll ask in a minute, but the slab is sort of integral with the walls. What was the thinking there as opposed to letting the walls be restrained by shear keys and letting the floor lift up? Because you will get damage there, right? And it's going to have to be inspected, and the extent of out of plane motion may change that form of damage. Why was it done the way it was as opposed to what you had done in the orthogonal direction, where you can isolate the floor basically from the wall and avoid the slab uplift?
So we had an industry advisory board for that, and it was in some ways not necessarily about coming up with a perfect solution, but also proving solutions that had been used in practice. So that was why we did the different things in the two orthogonal directions, is trying to there was two designs that had been used in practice in New Zealand. So I was trying to sort of prove them both. It was a balancing act as one of the industry advisors had said, we don't want to try so many different things that we end up with a Frankenstein building that's so bizarre we can't make any meaningful conclusions from it, but we wanted to try as many different things in the one building. Um, Overall, we did see more overstrength in the longitudinal direction, so that uplift of the floors and the deformations that go into the link slab did lead to more. That's not really considered in the design, so we did see a greater level of overstrength in there. So we saw a lower level of drift relative to the predicted target design drift, whereas that wasn't true in the orthogonal direction. There was definitely some cracking in that link slab as a result of that uplift. There wasn't significant cracking, and I don't think it was anything necessarily of major concern. But yeah, you are right. There is, I guess it was sort of proving both ideas.
No, I
And
see.
yeah,
Okay. Yeah, it makes sense from that perspective. So let me just read a question that John Stanton from University of Washington has, and I'm just gonna read it as it's stated here. Could you say more about the coupled walls? Were the coupled coupling beams, I'm sorry, were the coupling beams designed to rock?
excellent question. Something I probably glazed over a bit, but in that particular case, there was actually quite a novel damping device was incorporated into there. So essentially, there was two steel stubs that existed as came across where the coupling beam would be, and at the interface between them was actually a self-centering conical damper. So it was actually a conical sort of cone-shaped piece of steel that sat in the negative of that, and then there was a preloaded steel threaded rod that provided clamping force to that. So as the two cone the cone and the cup moved relative to each other, it was capable of bidirectional motion. So it wasn't just a linear damper. It could deal with in plane and out of plane motion. And as it displaced in either direction, the cone was displaced and it pushed against the preloaded. So the preloaded threaded rod also had some conical spring washers, the Belleville springs on there with the preload. So it essentially, as it displaced, those two, the cup and the cone, moved apart, which then reacted against the conical spring washers and then provided a restoring force there. So they were tested as a component quite extensively and then incorporated into that test. Not actually something that I was involved with. This was the University of British Columbia team that did all this. So they have published work on that, and I can certainly pass the paper on that if that's of interest. But that was, yeah, it was essentially quite a novel, potentially complicated, but quite well working solution to there's no yielding in the coupling beams themselves. It was all in that device.
Mhm. Yeah. Okay. Thank you, Geoff. Sorry. Any other questions from our audience or participants? So Geoff, I have a question. You showed damage at the toe. I mean, those wall systems are notorious for that, especially if you have bidirectional loading and the wall loads out of plane. You have that corner of the toe, like putting all your weight on your big toe or little toe. Um, was there any additional confinement or anything at that toe? Was it all standard all the way across the whole wall? Any precautions taken to control that extent of damage that was primarily just spalling, or is there any core damage?
Um, in the on the core wall or the
No, there was a perimeter walls where you had the
yeah.
damage at the toe, the
Um,
rocking walls.
so again, this was sort of trying to do multiple things in one building. The In the longitudinal direction, we had a lighter level of armoring, so there was an increased confinement around the toes, and then there's a steel plate which sat under there to provide, key contact. So the actual contact was steel on steel, but they're very quickly transformed into a reinforced concrete behind that flat steel plate. And then in the transverse direction, we had a much more heavy armoring. So if I actually run back through the slides quickly. Um, So this is the longitudinal direction. You can see there's just a steel plate at the bottom and then it goes into the reinforced concrete. But if we go back a couple of slides, this is the transverse direction. There's actually vertical steel plates up the outside of the wall.
That's it.
So we put a
Okay.
much more heavy level of armoring on the transverse direction and a lighter level of armoring in the longitudinal direction, because we weren't necessarily just trying to get a perfect outcome, but we were trying to determine, if you just go to a really conservative design and you armor everything really heavily, then you can get quite good behavior. But certainly the challenge we'd been thrown by the industry advisors was to try and say, well, let's not just come up with a design that's really conservative and works well, but let's see, try and say, well, actually, how conservative do you need to be and still get reasonably good response? So that was why the two orthogonal directions were used to determine different level of armoring and how well that worked.
Mhm. Okay. I guess what caught my attention too, since no one else has any questions, I have a few more on that rocking wall. What was that, 10 stories that was on the shake table with the outrigger system?
Yeah, it was actually nominally sort of a 30-story building, scaled down to one-fifth scale, but
Mhm.
getting 30 individual floor slabs and mass blocks in there was just sort of becoming too complex. So essentially every three floors was kind of lumped together to a single mass block, a single
Mhm. So
support frame.
the only gap opening was at the base of the wall, or was it segmental along the height of the wall as well, or only at the base?
So there was two sections to the wall. That was just basically a shipping thing because that wall was actually constructed in Canada and then shipped to China for the test.
Mhm.
But those walls were welded together. So there was a steel plate at the interface and they were welded rigidly at them. So for the purpose of the test, it was designed to mimic one continuous wall section without a hinge.
Because when you get walls, rocking walls, it's really primarily the first mode you're controlling. I'm curious about the higher mode effects on that wall that was tested. Maybe that data is still being looked at, but were there any pronounced effects, particularly, the accelerations can still get large in systems like that because the rocking only controls the first mode. Was there any assessment of that, or have they thought about putting segmental joints along the wall to try to control the higher modes or some other means of doing so?
Um, in that particular test, no. There was definitely higher mode effects in there. You could probably see that a little bit in the video, but um, we're probably still digging into that data because that test sort of wrapped up
Mhm.
late January, so we're sort of still relatively in the infancy of analyzing all the data from that. But yeah, that particular test didn't employ any of those sort of multi-mode
Okay.
isolation.
Yeah, yeah. I
Um,
wasn't being critical. I was
yeah.
just a little bit curious. It looks like it's a good set of data. Is that data public domain, or is that data
Uh,
going to be archived?
so the reinforced concrete test is quite extensively archived and it's available on DesignSafe. The robust steel test, so that was finished in March last year. So it does actually, when you've got like the you've got 300 channels of data coming off, and we had multiple data acquisition systems go through a synchronization process, and it is actually quite an extended period to just document and process that data to the point that it's usable. So I think
Mm.
the intention is to upload that with time, and then the same thing with the reinforced concrete coupled wall. That with time, there would be probably an intention to to upload that as well. But certainly the first building, the reinforced concrete one that's on screen now, that data is available. It's already on design
Okay.
stage.
Yeah, yeah. Thank you, Jeff. 'Cause-
I do
sorry.
know there's a few questions on the Q&A. Um,
Yeah, I'm on the chat, but there must
Yeah.
be a Q&A here, so I
So
missed that.
Jim, I have the Q&A. If you guys want to look at that, and read them on your own. I'm
Yeah.
okay with that,
So
'cause I do have to go to that experiment now. So I was going to hopefully you guys
okay.
can lead the rest of the presentation, or I mean the questions.
Yeah, so yeah, thank you, Tom. I'm glad you noticed there. I was paying attention to chat, not Q&A. So the Q&A, let me read the question, Jeff, and you can answer. So, anonymous, so we don't know who's asking, but it's fine. So can you simulate test experimental results with any numerical proposed available program? So I guess it's has someone developed an analytical model that could replicate the experimental results? I think that's what it's asking. And if yes, what programs?
so we had Anchi Gu, who was actually a PhD student at Tongji at the time we did this test. So the test was actually completed in very late 2018 and very early 2019. And then she completed her PhD at Tongji and came to Canterbury for 3 years as a postdoc. She's now back in a tenure track faculty position at Tongji, but she actually, a big part of her postdoc was looking at modeling, particularly the overstrength in the longitudinal direction. There was the overstrength from the floor interfact, so basically outer plane floor effects. So she had looked quite extensively at modeling that and the modeling strategies to capture the overstrength that came from that. So she used both ANSYS and Abacus, and she also did some analysis in OpenSeas as well. She has published a couple of papers specifically on that. So it's looking at the building itself, but then the outer plane floor effects, because that was the big contributor to the deviation between the experimental results and the simplified models. So um, that yeah that there is a couple of journal papers on that which just cover the modeling strategies that she's applied, and I guess if should put my email on here, but if someone can email me, I'm happy to send them those papers with the details.
Okay, yeah, thanks. And so I'll answer. Sorry, you'll answer the last question, Jeff. I'll state it here. It's from Mah Mahdad. I won't try to pronounce. I apologize the last name, but let me just read the question here. So, in the concrete building with rocking walls in two directions. Okay, so in one direction the wall was connected to the floors, and the other direction was not. So the question is, did you see any displacement differences in the two directions, since you have larger mass in one direction in comparison with the other? Is the basic question. I guess it's the bidirectional response.
So yeah, we did see quite a difference in terms of in the transverse direction where the walls were isolated. We saw displacements which were actually pretty similar to the what the design predictions would suggest. And in the longitudinal direction, we saw them consistently coming in at maybe sort of 80% of what the drift target was when we subjected to that demand. So we essentially went through a design process and we matched the earthquake motions we applied to the building to the hazard curve that the code assumed. So um, that was really attributed primarily to the overstrength and the extra. There's a little bit of damping as well that came in because of the fact that the the extra floor effects. There was also a few other things like if I go back in to the building here in the transverse direction, we had dampers installed at the wall base, and then we also had dampers at the slotted beam connections, so the slotted beam to column connections. In the transverse direction, we had dissipators at the dampers at the wall base, but we also had them at the beam to column and beam to wall connections. So in the longitudinal direction, there was a larger number of dissipators, but then the yield force on the dissipators was higher in the transverse direction to try and counteract the fact that there was a lower number of them. So, I guess what I'm saying is that there's actually quite a lot of differences between the longitudinal and transverse direction. We have gone into the modeling of where that comes from, but I guess there was essentially 16 beam column or beam to wall connections in the longitudinal direction, and only 8 in the transverse direction on each side. Sorry, yeah, 8 in total in the transverse direction, 16 in total in the longitudinal direction. But then all the dissipators were of different force capacities to try and accommodate for all that. So that I guess probably rambling a little bit here, but it's a more complex answer in that we did aim for sort of total the same amount of damping and everything in the two directions, but there's a lot of moving parts in that comparison.
Okay.
But
Well,
yeah,
yeah.
probably the biggest thing was that there was the level of overstrength relative to the design prediction was much lower in the transverse direction with the isolated walls than it was in the longitudinal direction with the coupled walls. And consequently, the displacements were larger in the transverse direction.
Mm, okay. Yeah, yeah. Thank you, Geoff. So, everyone thanks you for your questions. Sorry for I thank the audience for the questions, but thank you for the the answers. And I think probably we should wrap up the webinar. What I want to make a note of that, Geoff, if you don't mind, maybe you could put your email address in the chat if people want to contact you. They can always email our site. We're obviously if you registered, you can access Design Safe. You can access our webpage, but that way they could also contact you. And so Geoff will put his email address that if you want to contact him directly, it's right there. That would be a convenient way of doing so. And so with that, Geoff, wanted to thank you, for volunteering to do this. I thought it was quite interesting, and I'm sure there's questions that will come up that people will contact you, and wanted to thank you and clap here for you. So with that, I wish everyone a good rest of their day wherever you may be, and stay tuned. We try to have these quite often, and look forward to hearing more in the future about your work there, Geoff.
Well, thank you very much for the opportunity to present and for hosting me here at Lehigh.
Yes, yes, and thank you again for everyone for attending there and spread the word. We're trying to expand our audience here. Okay, thank you. I'm going to go ahead and stop the webinar here. Thank.